One thing I want to point out, the email I sent you guys did not have 3.4 related rates on there. So I apologize for that. It's been uploaded to Blackboard with that added under study guide. So if you go to class notes, study guide, calculus, exam 3 study guide, right there. And it includes 3.4. So if you're studying and you looked at the study guide and kind of thought, oh, 3.4 is not going to be on the exam, it is going to be on the exam. So surprise. No, I apologize for that, but it's there. Another thing I want to comment on, if you go to class notes, I've uploaded an Excel file. It's nothing fancy, but a lot of times Blackboard just gives you a raw score. It gives you, these were the scores I have recorded for quiz 1, quiz 2, quiz 3, homework, written homework 1, written homework 2, things like that. And then Wiley has your Wiley grade in it. And so the percentage of your grade broken down here. And then this allows you to manipulate anything that's in yellow. So let's say you got a 75% on exam 1. Your current grade, so a lot of times students ask me, what's my current grade? Well, it depends on kind of the stuff. So you can calculate this on your own. I mean, you guys are in calculus. You should be able to calculate weighted scores. But this just kind of helps you, especially towards the end of the semester when you're like, what do I need to get on the final to get this grade to be what I want it to be? So after we take the first exam, if you didn't do anything else in the class, if you got a 75 on the first exam, you would have a 7% in the class. So, quizzes. We've taken 7 quizzes, I believe. So if you average those 7, let's say you had an 85 on your quizzes, that tells you where you're at. Online homework, let's say assume you're doing really good on online homework. Those 5 attempts come in handy and you're on top of it. Some notes here. Only change the cells in yellow. If you change other cells, it's going to potentially, because all these, the formula is not difficult whatsoever, but they're there. So if you delete other cells, it might change some of the things in green. But if you only change the yellow cells, everything should work out okay.
Excuse me, so you would drop 3 of online assignments?
Yes, at this point, I'm going to drop 3 of them. So if you go in your online and say, oh, I didn't do 3 of them, but I've gotten hundreds on everything else, you can say your online homework is going to be 100. Enter as a percent. So if you're saying, oh, I got 75 here, it's going to be like, oh, you have this insane percentage. So enter as a percent, 0.75. So you got your percent here. So let's say your written homework, you haven't been too good about turning in written homework. Let's say you've only done about half of them or only gotten half your points. You can say you got 50% there. Exam 2, we've already did, let's say we bombed that one, we got 41. So this would be your current grade. Not too bad, right? You're surviving. Honestly, this is what's saving you. This is 15% of your grade. So quizzes, and then the online homework's 15%. Let's say you have not been doing your online homework, or you've only been doing about half of it. It changes your grade quite a bit there. And then obviously if you didn't do anything else, you're not going to pass the class. So exam 3 is coming up. So let's say you got a 60% on exam 3. And then once you have exam 4, let's say you have 80. This is where kind of the final exam comes in. Your current grade, but if you get a 0 on the final, that's where you're going to be. Let's say you got a 66 on the final. After everything is entered here, the current grade and the grade, if you didn't do anything else, is the same, because there's nothing else to do. But on top of this, I don't have it automatically replacing your lowest exam score. So your lowest exam score being 41%, that 66 would replace that. And you will have to do that by hand. My Excel file is a little more complicated than this because it takes in account other things. So it automatically does it. But if I come in here, you can see it doesn't change your grade that much. So you can come in here, well, what if I was to get a 40 on the final? So I wouldn't be passing. If I got a 50, well, then this 50 would replace this 41, and I would have a 61%. So a lot of times the setup is you can get a 50 to an 80 and keep a C, but you would have to get a better than an 80 to get a B type thing. Question?
If I know our final quiz is our lowest exam score, but it won't do that if we do worse on the final.
Correct, exactly. Yeah, so if I come in here, yeah. So if this was 41, yeah, if you come in here and do 40, it won't replace anything. It will only do it if it helps you. But if you come in here and get a 90, that 90 is going to replace this 41, you're going to have a 75. But then if you have 100, 79. So this person's like, even if I get 100 on the final, I'm not going to get a B. But I have to get at least a 50 to get my, what was that? 61%. So you can kind of see how this is going to show you. Majority of the people are pretty locked in to what they're going to get. The ones that really help them, if they've done really good, let's say they've done 75% on the exams, and then let's say they've done 21%. What really helps them here, if they come in here and get 75, then this becomes a 75, and it changes their grade quite a bit. But honestly, that doesn't happen too much. But that's there. So this is posted on Blackboard. It's an Excel file, so open that. Open Excel, enable editing, and then I have like a sample one here, but you can change any of that.
Which tab was it under? On the
Notes.
notes. Okay.
I figured you guys go,
Makes sense.
I don't know, that would, and then the study guide's also there. And then the last couple notes from chapter 4 will be there. Then I'll make one for chapter 5 after the exam. So I think I walked you guys through the calculus resource page under my organizations for final exams. At this point in the semester, it's a good idea to be somewhat familiar with the final exams. So if you haven't been looking at them to study for this even next exam, it's a good idea. So all final exams are here, and then the solutions are also here. Question?
Are we going over any of the stuff for the test tomorrow today? Or?
Yes, that's what we're going to do for the rest of the time. I just wanted to kind of throw out those resources because I have a lot of students the last couple of weeks come to me desperate. I need to know my grade. Well, I don't want to do. You know, you have all your information to find your grade. If you don't have your quizzes, it's posted in Blackboard, the raw scores. So go through and add up the best 8, and that's your quiz grade. Divide that by 150, and that's your quiz grade. Question?
Do you know how many quizzes we have left to do, possibly?
I will give 10 for sure.
Okay.
So
You might do more than that?
possibly. This depends on. Towards the end, it's kind of hard wrapping everything up, giving that 4th exam, preparing to throw quizzes in there. But it might be possible where I put a Wiley quiz on or something. All right, so questions. Did you have a question? Or
Yeah, I just on those where we have the like a box
Mhm.
that I can open top. I just have trouble finding the second equation. Sometimes like I know the
well, usually they'll give you a specific volume,
uh-huh.
right? And the volume would be XXH.
Yeah.
Because a lot of times your box is square. And it has to be square to be able to do the problem because we only have 2 equations. We can only have 2 variables. So the first equation would be volume, and you understand that. The second equation, you're just going to have to draw a picture and find the surface area. And if it has to do with cost, you have to divide up how each side it costs to make it. So drawing the picture here, I have a square base. I have some height in my box, another square. Pretend this looks decent. Imagine, you have to use your imagination pretty high. Getting crazy. So then if this is x, x, h, then the surface area is going to be, if it's open, an open top, and depending on how it's set up, so this would be the top. Because if it has a square base, then the top would be xx. So the surface area would be x squared, because there's one bottom, plus 4xh, because there's 4 sides, and the sides area is x times h. Right?
Okay.
Does that make sense? Now, if it has to do with cost, if the cost of the top is, maybe the cost of the top is $4, and the cost of the sides are $2, then you'd have a little bit different equation there.
Would you just put a 4 and then a 2?
Yeah, you would put a 4 in this problem, and then you'd have x squared times 4, because it would cost me $4 per square inch, and it's x squared square inches. So how much it's going to cost me is 4 times whatever that is.
I guess I just have a question, because sometimes we're given the volume, but we're not given another number. How do we, if we're not given the surface area?
You won't be given the surface area, because that's what you want to minimize in the case of a specific volume.
Oh,
So this is the problem that but you need to get it only in terms of x. So your volume, being x squared times h, is some set number.
Okay.
So you use this to get h in terms of x, so h is this set number divided by x squared. Then you can plug this into the equation for surface area so that you get surface area as only a function of x. Once you get that, you differentiate that, you set that equal to 0, you find a critical point, and you confirm that it's a maximum critical point or a minimum critical point.
I guess I tried to do it almost backwards.
Okay.
So, okay.
Does that make sense now?
Yeah.
You'll always be given enough information to have two equations. And then the one equation that's given, if it's a set area or set volume, you use that equation to solve for one variable in terms of the other variable. You can pick either one. This case, it's easier to pick x, or to solve for h in terms of x, because when I plug this in, it's a lot easier to deal with. Then if I solve for x in terms of h, then I'd be plugging in a function of h, differentiating that function of h, which is doable.
Yeah.
Computationally, it's a little more fractions to deal with and squares and things like that, but definitely doable.
So the problem will say something like, you have this many feet cubed. or
Yeah,
whatever
a lot of
for
times,
volume,
Yeah. So
And then you need to find, it'll ask for the maximum surface area,
minimum.
or minimum surface
Yeah.
area. Okay.
Yeah, they'll say, or they might ask for the minimum cost, because cost is a lot of times associated with surface area. If I have to build a box, then it's going to cost me per square inch.
But then it usually says maximize volume, right?
Yeah, generally, if I have a set surface area, or if I have a set amount of money to spend, and I want to maximize my volume, I want to know my dimensions of my box.
Okay.
So yeah, you can look at it various different ways. But if you understand the concept of getting this equation, getting two equations, writing one of the equations in terms of the other variable, right? Because here we just have a number over a variable. Plugging that back into the equation, you want to either maximize or minimize, and then go through the process of maximizing or minimizing it. Any other questions to begin?
I was just wondering if you could go over a L'Hopital's rule one that is, I guess, well, of something that we'll see, not something that's, okay, I see clearly that's 0 over 0 already, or...
And you might see something like that, especially in the final exam. It comes up a lot of the times where generally there's two of them on the final exam. One straightforward, show your work, apply it, but you pretty much know what it's going to go to. And the other one might be a little bit higher level, or you might have to apply L'Hopital's rule twice, or you might have to manipulate it before you can apply L'Hopital's rule. So if we look at L'Hopital's rule section, I mean, we have various different examples to go about. You know, this one's pretty straightforward. This one, this is going to infinity, so I have infinity over infinity. It's pretty straightforward, but it is a true L'Hopital's rule problem, right?
So right now, the number 17, that's already informed infinity over infinity, right?
Well, yes.
And so you can immediately apply L'Hopital's rule.
Yeah, but
What's
it's
it
also a polynomial over an exponential. We know a polynomial over an exponential goes to 0. So you could apply L'Hopital's rule 100 times.
Exactly.
I know it's 0.
Yeah, but yeah. So, but if it was flipped, if it was this one, this goes to infinity. It's infinity over infinity, but goes to infinity. This is infinity over infinity that goes to 0. But you have to give some reasoning. So you could just say, from the theorem, polynomial over an exponential as x goes to infinity is 0. And from the theorem here, an exponential over a polynomial goes to infinity. But in this case here, this is almost in that form, but you need to write it as x over e to the x, which is going to go to 0, but it's not quite in that form yet. Here, this one I gave you on your quiz. which was in the form 1 to the infinity power. So
ln.
you have to use the natural log there. Another type of problem that you could possibly see that is a little bit different level is when you have something like this. When you have infinity minus infinity. And remember, I multiply by the conjugate, and then don't try to apply L'Hopital's rule there. Just use the indicate here. Or you can divide top and bottom by the absolute value of x. Here, in this case, I have infinity minus infinity. So, going about that one, so multiplying by that's going to infinity.
The X on the bottom.
Divide through by x, or
Take text.
there's not an x I can't pull down that x.
Since it's mine.
So here I want to find a common denominator. Here I'd find a common denominator and have the fraction of infinity over infinity or 0 over 0. In this case, I have x to the sine of, let's see if I can zoom in here. You guys can see this.
For 34, couldn't you just combine those over x squared?
34?
Yeah. You could find a common denominator, or you had a common
Right, 34.
denominator.
Yeah, you can combine them. So I have 1 minus cosine of 3x over x squared. Cosine at 0 is 1, right? Cosine, yeah, so 1 minus 1 is 0. So this is 0 over 0, but you would need to combine that. Here we have x sine of x. So sine at 0, 0. So I have 0 to the 0 power, which is indeterminate. So I'd use natural log here. So I have sine of x times ln of x, which you might have that one. I think that one is actually somewhere else in your homework. This one is going to simplify to ln of x over x, which is the exact same thing as this one, right? But then when we get the answer here, it's going to be the limit of ln of y. So your answer is going to be e to that number. So a lot of these are very similar. They're just different forms. Your forms are pretty straightforward that you're going to have. It's not going to be anything too crazy. I think I gave you this one somewhere. Anytime you use where you're taking the natural log of a function to simplify it. But if it's over here, there's one on a final exam that I did in the previous class that didn't have anything to do. So we talked about this one in the previous class. It has nothing to do with e. This is an ln of a function divided by ln of a function. So this is infinity over infinity. It turns out my answer here is 2. It's not e squared because it doesn't have anything to do with that. I never took the natural log of it, yeah. But sometimes students will be like, oh, there's a natural log there, I have to put e. But that's only when you say, this is not indeterminate, it's maybe 1 to the infinity. So I can't apply L'Hopital's rule directly, but I can say this is y, take ln of y, then I have 0 over 0, or infinity over infinity, right? Because I have something... So I have something when I have, the limit as x goes to infinity of f of x times g of x, and let's say this is type 1 to the infinity, I really don't know what's going on there. So I can let y equal f of x to the g of x. And then I have ln of y is g of x times ln of f of x. So then in this case, I might have 0 times infinity. In the case, I can write this down in the denominator with a negative exponent, and I'd have 0 over 0 or infinity over infinity. So I'm finding the limit of ln of y. But to get y by itself, I would have e to that answer to get the original limit. Does that make sense? So yeah, in the case where you do that, your answer will always be e to the limit of ln of y, which is some number. But if you don't make the extra effort to do this, then e doesn't exist in your answer anywhere. Okay, because sometimes students will say, oh, there's an L in the limit, I have to put an e, and that's a common mistake there. Okay, so just to kind of run through some of the points, 3.4 related rates, pretty straightforward problems, either a ladder problem, an oil spill problem, a softball problem, a balloon blowing up problem. Nothing too crazy with like the radius is changing with respect to the height, or there's no cones or anything too crazy there. So
I just have a quick question. There's, I remember when we were going over this in class,
Mhm.
trying to review in the lectures online, obviously, that there's a syntax that the book uses, and then there was like a syntax that we used in class that was much simpler. And I'm having some trouble.
for related rates
When you
or
do, yeah, when you're doing
3.5?
the, like, no, it's 3.4. It's when you, like for example, the ladder problem. So you're given the rate at which the top of the ladder is moving down, and you know that you want to find what the rate of the foot moving away is when the height is 6 or
Yeah.
something like that. And so you've got like d of a, or dA dt and dB dt or whatever. The book's syntax is
Like d theta dt?
no. What I'm trying to say is that it's like
I don't see. This is all just x and y's.
yeah, like right there we go on that baseball diamond problem. So right where it says differentiate both sides of this equation
Yeah.
with respect to the t. See how
Yeah.
it says dx 2x times dx dt.
Yeah.
I feel like when we did this in class, there was a simpler way of us putting that.
I don't think so.
I thought that we did it differently the way that it was written.
This is 3.4. So if I go to the notes from 3.4, in this section, 3.4, did a couple days on it. Oh, that was on the different problem. This strategy.
Yeah, it's the very next, yeah, the second day of it. There you go.
So I called it A and H because,
No, I
Yeah.
understand that. But
so
what
then
I'm
I
saying
have
is,
the same thing they have.
how do you get from that step there to the next one down?
Here?
Yes.
Well, I just solved for dH dt. So I divided through by, I have, if I wanted dH dt by itself, I divide through by 2h on both sides. So then I have 2a over 2h, the a stands for a over h times dH dt.
And that's when you plug in the rates that you know already.
Yes. You always wait until after you differentiated to plug in everything you knew. Because we say here, we're dealing at this when a is 20. If I play a equals 20 in here and I try to differentiate it, I get 0.
Yeah, exactly.
Question.
So when I did that, and you say don't plug anything that you know, I did plug in the 90.
Don't
so
plug
then-
anything that's changing.
Okay.
90 is not changing.
Because
Yeah.
then I was like, we don't have a, you know.
Yeah.
Yeah, sometimes you need the other leg of the trunk. Like in
Yes.
that case, you need the other leg of the trunk.
Yeah. So anytime like on the ladder problems, the ladder doesn't change the height of the ladder, the length of the ladder doesn't change, but everything else is changing.
Yeah.
So So you don't plug in anything that's changing. Yeah. Because here A is changing, but we want to specifically talk about the rate of change to home plate when A is 20 feet or
Yeah.
inches or
Set it
whatever.
fixed,
Yeah.
whatever. Okay. Thank you.
So this is important. If you use x, it's perfectly fine, but be careful, you're taking the derivative of x with respect to t, so you have dx dt, not 1. The derivative of x with respect to x is 1, but the derivative of x with respect to t is dx dt. You need that because that is that's part of the related rates. Okay, so I think that's pretty straightforward. Local linear approximation and differentials. Formula 1 and Formula 2 say the same thing. Formula 2 uses delta x. You don't have to use that. I know Wiley kind of forced you to replace it. It means the same thing. You can use either one of these. And if I want to approximate a function at a point, I take a point of the function I know, plus the derivative of the point of the function I know times the point I want to find minus the point of the function that I want to.
So the last
that I know.
point, if you're not using the other formula, should that x minus x naught be absolute value?
No.
So if we had 2.98 is our one that we didn't know, minus 3 of the value we used, we'd get a negative number.
Yes.
Okay, so our final answer would be negative as well.
It wouldn't necessarily be negative. It's just because this number is going to be greater than this number, so you're going to subtract to it. It's the difference in an underestimation and an overestimation.
Okay.
So if I take
Okay.
a point like this,
Because you're adding them.
and I say, you know, if I point, maybe I have the equation of the tangent line, I don't know, at this point is here, that this point is an overestimation to the function. I guess this point is still an overestimation. So yeah, the book on this local linear approximation, they give you this function, and that comes straight from the book. That I'm approximating it, and it's x minus x naught.
Because I was looking in whenever I multiplied
And
your f of x naught times that negative.
Yeah.
So that's just going to be a smaller number than your x naught.
I think, and not necessarily, it could be larger. I could approximate 1.99 around the point 2. I could also approximate 2.01 around the point 2. So it just depends on if your approximation is a lower approximation or if it's a higher approximation. So if I want to approximate 2.01 around the point 2, then this is going to be positive, 2.01 minus 2. But if I want to approximate 1.99, this is going to be negative, because I have 1.99 minus 0.2. But the delta x is still going to be positive or negative.
Plus or minus.
Yes, yes. Is it over it or is it under it?
Okay.
So yes, that's important there. So those three things will more than going to show up on the exam. You're going to have to do a related rates problem. You're going to have to do a L'Hopital's rule problem. You're going to have to do a local linear approximation problem. And then chapter 4 is not as broken up as, 3 is this type of problem, this type of problem, this type of problem. Chapter 4, 4.1, 4.2, and 4.3 are all on graphing, and it's saying the same thing. So to find the graph of the function, you find the x-intercepts, the y-intercepts, the vertical asymptotes. When's it increasing, when's it decreasing, when's it concave up, when's it concave down, and where's the inflection points. That's a lot of material. That's a lot of information. So I might ask you to do any one of those things, but I'm not going to ask you to do all of them on one problem. So 4.1, 4.2, and 4.3 know how to do a first derivative test, know how to do a second derivative test, know how to find a maximum point, a minimum point, an inflection point. Question?
Is there any question where we're given all of the information we have to graph it?
Possibly. I haven't made the exam, so I'm.
Oh man.
I haven't made the exam yet, so in the past I've given ones where here's all the information, graph it. In the past I've said graph an increasing concave up function, graph a decreasing concave down function, or I would say graph a function where the first derivative is positive and the second derivative is negative. Where I don't say it's concave up, but you need to know it's concave up or concave down. So there will be some aspects of graphing on the exam, but it's pretty straightforward. Like, I might give you a first derivative test and a second. I might give you information from it and say, where's the maximum point? Where's the minimum point? Where's an inflection point? Where's the vertical asymptote? Where's,
Give us a picture of a graph and
Maybe.
ask us what
It's the same thing Wiley's done, right?
Yeah.
They give you a picture of a graph and ask for the information,
Yeah.
or I could give you the information and ask for you to graph it. Be able to go both ways there. Question?
Can you review quickly there's 3 rules for horizontal asymptotes of rational functions?
Horizontal asymptote of rational function, so this is really kind of in 3. When it gets interesting, because a polynomial is continuous everywhere. E to the x is continuous. All these things are continuous everywhere. So really when you have a polynomial divided by a polynomial, you get a little bit more interesting. So for a horizontal asymptote, I'm just going to write this on top of here. A horizontal asymptote, we have, let's say, ax to the m plus something over bx to the n plus something. Sorry. Whew. Okay, so when m equals n, what happens? The horizontal asymptote is, very good, y equals a over b. When m is greater than n,
It's infinity.
it's actually infinity, but more so we can test oblique asymptotes, which you probably didn't talk about until this point in calculus, right? When the power of x in the numerator is greater than the denominator, it's going to go off to infinity. But it might approach some other function like x squared. X squared goes off to infinity, but my function might approach that as I go off to infinity. You know, a quick example, if I have x cubed over x, obviously that's x squared, right? But it's a polynomial over polynomial. The limit as x goes to infinity goes to infinity, but more so it's approaching this oblique asymptote x squared. Does that make sense? And this is just a pretty quick example of a power of x in the numerator being greater than the denominator and having oblique asymptote.
And if that's what we'll say is there's an oblique asymptote. in this
Possibly, I might just classify 5 or 6 functions, classify the ones that have which ones have oblique asymptotes. And there might be A, B, C, D, E, F, and G. So you can say A, F, and G have oblique asymptotes. Finding it, you're going to use long division. So going to
So it's not
4.
0 like it normally was.
Well, 0 happens when the power in the numerator is greater than the denominator. Then you have a horizontal asymptote at y equals 0.
Sorry,
Horizontal.
Which one do you mean as the numerator and the denominator?
What?
Which one do you mean as the numerator and the denominator?
N's the power of the denominator.
So if the denominator is
It's greater than the numerator.
Yes. If the power of the denominator is greater than the power of the numerator, the horizontal asymptote is at 0. If the power of the numerator is greater than the denominator, you have a potential to have an oblique asymptote. But it's going to go into, it's not, the horizontal asymptote is none, but you could have oblique one. Horizontal would be none, because you wouldn't have a horizontal, but you would then look at your oblique asymptotes, right? So if we're just classifying horizontal asymptotes, this would be none. You're correct. But you would want to test oblique if they ask for it. And that's the case. This is when oblique asymptotes happen, when the power of the numerator is greater than the denominator. Question?
So what about the limit of,
The function?
yeah,
And this is related to the limit of the function. If you have a polynomial over polynomial, and you take the limit, you look at the highest power of x in the numerator and the highest power of x in the denominator. If they're the same, they cancel, and you get a over b. If the power of the x in the numerator is greater than the denominator, then it goes off to infinity, and you have no horizontal asymptotes. If the power of x in the denominator is greater, then the denominator goes off to infinity, and you have 0 is your horizontal asymptote. And approaches 0. So they're related. This is kind of the college algebra approach to say, oh, the power of this. But it's related to calculus, the end behavior.
so when is it none again?
What?
When is it none?
When the numerator is greater than the denominator. And in that case, you have a chance to have an oblique asymptote. So in this case, you have no horizontal.
Is it that you have oblique or horizontal asymptote?
What?
Like, is it that you have oblique or horizontal asymptote?
Correct. Yeah, you won't have both.
Are you guaranteed to have an oblique asymptote in that case?
Yeah, I mean, because you can always do long division, so you're always going to get something. I might not care too much if you have it. So if we look at these examples here, all these examples are of oblique asymptotes, and if you notice, the power of the numerator is greater than the denominator in this case. Right? So if I do long division, they already did the long division. So the limit as x goes to infinity goes to infinity. But this function, as it gets really, really large, is going to approach x squared. So after a certain value of x, I can kind of negate it. I can kind of forget about this and say, oh, it looks like x squared. X squared goes off to infinity, so I don't have a vertical asymptote. but it's approaching this x squared. If it looks like this, then you need to do long division. Right? So if I do x squared plus 1 divided by x to the 5th, I'm going to get a polynomial there. So whatever I have, and then I'll have a remainder, and then that remainder is going to go to 0, and whatever I have here will be my oblique asymptote.
You're in that long division. You're attempting to get down to quadratic form, right?
Not necessarily quadratic. What I'm doing here is I'm taking x squared plus 2, or x squared plus 1, divided by x to the 5th. Right, so here I have x cubed.
Right.
Is that what you're going to ask?
Yeah, you said it the opposite way.
Oh, did I say it? I'm sorry.
Yeah, you wrote it the way that it is there, but yeah, I was throwing me off.
Oh,
So was like,
I
no, that's not
apologize.
divided by.
It's
It's divided.
long week. Okay, so does that make sense here? So you're going to be able to write this x to the 5th over x squared plus 1 as x cubed plus, if I need an x, possibly something here, plus something over x squared plus 1. So this would be your
Right.
oblique asymptote.
Okay.
Would you have a vertical asymptote here?
No.
No. If it was negative, it would be plus or minus 1. If it was x squared minus 1, it would be. Would you have a vertical asymptote here?
Yes.
Yes. At 2, right? At minus 2.
Yeah.
At minus 2.
Yeah.
Vertical asymptote being up and down, right? Horizontal asymptote you wouldn't have, but you would have a oblique asymptote there. Here you have a vertical asymptote, but x equals 0, x equals 0, x equals 0, and x equals 0. So you can have both a oblique and a vertical asymptote.
Oh, okay, because it's divided by. Never mind. I see.
Yeah.
And how do you draw the
You graph what the function would look like, so if it was like x squared, and you just like a dotted line, and your function is going to approach that. So if I know my function is something crazy, but I know it has an oblique asymptote at x squared, just like I would, this is kind of the outline. So my function might do something like this, but I know it's going to approach that. It's going to go off to infinity, but more so it's approaching x squared. Right?
What if your oblique asymptote is something crazy?
It won't be.
Okay, so
But theoretically, if it was, you could use calculus to graph the oblique asymptote by differentiating the oblique asymptote, setting it equal to 0, finding the critical points, and then finding the concavity and finding the x-intercepts and the y-intercepts. So you can see how these problems can get crazy, right?
But we don't have to do that.
No, it will be pretty straightforward, yeah. You're not going to
I'll
have
call you out on it.
Huh?
I'll call you out on it.
Yeah, it will be pretty straightforward. And more, I mean, there's not going to be, think about this. I have 50 minutes. I have to give you a related rates problem. I have to give you a applied maximum and minimum problem. I have to give you a L'Hopital's rule problem, local linear approximation, and something on graphing. So I can't, take up 20 minutes on a graphing problem, which would take me quite a bit of time to get all that information. But you should be able to look at it and say, what's my x-intercepts? What's my y-intercept? What's my inflection point? But not graph at all.
X-intercepts, y-intercepts, and your vertical and horizontal asymptotes are all from your original function, right?
Yes. And then critical points would be from your first derivative, and inflection points would be from your second derivative. When both of those equal 0 or undefined. Because you could have a cusp, a graph of function like this would be when the function is the derivative of the function is undefined at 0, but the original function is defined at 0.
Is that the first or second derivative?
First, yeah. First derivative is undefined there. And that brings us to maximum and minimum problems. 4.4 and 4.5 are the same thing. 4.4 is just find the maximum and minimum. 4.5 is maximize and minimize something that doesn't give you a formula. So you have to come up with a formula by yourself. So these are a little harder to do because if you can't come up with the formula, you have no chance to do the problem. But I could say, here's a function, maximize it. Here's a function, find the interval of increasing, find the interval of decreasing, find the interval of concave up, concave down. You guys have been doing that, right? And then 4.6 is rectilinear motion. And we talked about this a little bit in more detail yesterday. It's the exact same thing you've been doing, but now it has a little bit more meaning. Here's a position function, find velocity. So I won't say when is the slope positive, I'll say when is the velocity positive. So you know that you need to differentiate that, set it equals 0, find the intervals in which my particle's velocity is positive, which would be when my first derivative is positive.
So outside of like squares and rectangles and circles, we don't really have to know volumes and like surface areas or anything like that.
No.
Right? Okay. So
Outside
as long as
of
we know
squares
those-
and circles, yeah, and rectangles,
Yeah.
they're
Okay.
good. And if I occasionally, sometimes the volume of a sphere comes up, I'll give you that.
Okay.
Question?
On the rectilinear
Motion?
motion, yeah, the speeding up and slowing down, we use the velocity and the acceleration.
Correct.
Okay, and when they're the same, it's speeding up. Okay.
Yeah, so that, I mean, but you've been doing that the whole time, finding critical points and inflection points. So, and then it's just looking at the intervals in which they are the same. So a lot of these are just polynomials. Differentiating a polynomial, setting that equals 0, pretty straightforward. Finding the speed, or finding the position at 1, the acceleration at 1, the velocity at 1, the speed at 1, being able to plug that back in. More so, it's more computationally annoying to evaluate a polynomial at a certain point than anything else. You know, you've been doing that since middle school, plugging points into functions. So more so than the notion of speeding up and slowing down is probably the anything new in that section. Any other questions? Yes.
When the book asks for the interval, when it's increasing and decreasing, it asks for a closed interval, or when it asks for when it's concave up, concave down.
It always asks
It
for open.
Interval, and then I don't understand what the difference is.
Okay, so there's really, it's just kind of a overall, style of what they define to be increasing and decreasing. They defined increasing as getting larger or equal to what you started at, right? So a constant function is increasing and decreasing. So it's their definition of increasing and decreasing. That's why you can include the endpoints. On my third exam and on the final exam, it's straightforward. As long as you have the right interval, if you include it or don't include it, it's fine. If I say give me an open interval, write an open interval. If I say closed interval, write a closed interval. But if I just say interval, if you have, if you have 0 to 3, this would be correct, and this would also be correct. The only thing that would not be correct if I had something like 0 to infinity, infinity to 3. This is the same, and this is give you the same, but this would not be correct.
Yeah, 'cause you can't just close interval.
You
on
can't
infinity.
close infinity. Yeah.
But the correct rules are when it's like increasing or decreasing.
It's closed.
But
Concavity is open. Because the change in concavity has to do with the change in slope,
Yeah, like
right? So if I have something like this, I'm going from a positive slope, right, positive to 0 to negative. My slope is negative. My change in slope is negative. I'm decreasing, right? If I'm positive 5, 0, negative 5, this whole time I'm decreasing my slope. I'm concave down. So the derivative is negative.
And that's an example of an open.
Correct.
Yes.
Yes. And then this point would be a maximum. So when the second derivative is negative, I have a maximum point. So if I have a critical point in that interval, I have a maximum point. Does that make sense?
Yes.
So, yeah, maximum minimum problems. If you look at old final exams, that will give you an idea And not all of them have a maximum and minimum problem. Find the absolute maximum and the absolute minimum of this function on this interval. Well, first off, you have to see if it's defined on that interval, and it is, so we don't have any issues there. But differentiating this function, we have to use the quotient rule. Set that equal to 0. The denominator is never 0, so I don't have a problem. Focus on the numerator, find the critical points in this interval, and then test the endpoints and the critical points. And then here it just says absolute max, absolute minimum. So you're using the value of the function that at the largest value of the function and the smallest value of the function. What?
It's not going to be X.
It's not going to be X.
It's going to be like
It's going to be the, so let's say if I plug in 0, I get 0. 0 could be the max. No, it could be, more than likely it's the minimum because this function is never negative on that interval.
So in the first derivative, you'll find your critical points.
Mhm.
And then when you test above and below them, you're going to find where it's increasing and decreasing.
Yes.
And you do that in the derivative. You plug those numbers on either side of it into your derivative function to
Correct.
find that, right? And
Yes.
then to find your actual max and min, you plug your critical points into the original function.
Correct.
So you
Yes.
wouldn't have to use them as inputs, right?
You would not.
Just take.
You wouldn't care if it's a relative maximum or relative minimum because you have a close interval.
Yeah.
So you don't have to do the first derivative test here. You say, let's say your critical point's a half. You test 0, you test a half, and you test 2. Which whenever is the largest that outputs would be the absolute maximum in that interval, and the smallest output would be the absolute minimum in that interval.
If that was an open interval, would that be a clue that the function was going to infinity?
Possibly. We really don't set up problems like that with the open intervals. If it could be possible that it goes to infinity, but it's possible that it just goes to 1. Right. So then you would have to test to say, okay, is this going to 1? And this maybe be going to 2. So the maximum point in that interval might not exist. It might. If it goes off to infinity on this side, infinity on this side in your open interval, you only have one critical point. That's where that one critical point is going to be the absolute minimum or the absolute maximum. So then you have to classify it, that critical point, as a minimum, relative minimum, or relative maximum. So a lot of times, the applied problems will be the open interval. And then you have to only get one critical point and verify that.
That's like find a way, like find whatever inputs you need in order to minimize your cost of manufacturing, for
Yes.
example. Or
Yeah.
the highest profit on t-shirts sold.
Yeah, usually you want to focus on profit, and you have revenue minus cost, or production, revenue minus production. So you have this larger equation, differentiate that, set it equal to 0. Say, how many t-shirts do I want to make?
Yeah,
If
in
I-
order to,
yeah.
in order to get up on top.
Either to maximize my profits, because if I make too many,
Yeah.
then the production costs are going to cost me more than I can get out of selling them. If I don't make enough, then my revenue is not going to be maximized. So there's things there. All right. Does anyone have any other last minute questions? Our time's up.
Question
So.
about Wiley.
Okay.